This is part 2 of our examination of the processes by which mammals exchange thermal energy with their environment. In part 1, we looked at the processes of metabolism and convection conduction. Next up is radiation. The third and fourth processes both deal with radiation, but from different sources. What we're calling radiation in this section is simply electromagnetic waves that can transfer heat. This includes all forms of electromagnetic radiation. You probably remember from other science classes that we classify electromagnetic radiation based on its frequency or wavelength. Radiation from the sun includes mostly visible radiation and the longer wavelength infrared radiation, but also includes other types such as the shorter wavelength ultraviolet radiation. At the top of our atmosphere, the radiation coming from the sun amounts to about 1,360 watts for every square meter. That's roughly the equivalent of the heat from almost 14 100-watt light bulbs packed into a square meter. Luckily, the amount that hits us is not that much. The amount that actually hits an organism is going to be dependent on a number of factors, such as the time of day, season, latitude, and absorption by the atmosphere and clouds, and the organism's angle towards the sun. Because of this, for this section, the amount of heat from the sun is a variable that you will have to be given. The second part of radiation is the heat gained or lost to the surrounding air. All matter emits electromagnetic radiation. As long as an object's temperature is above absolute zero, it will emit heat in the form of radiation. Of course, objects at higher temperatures radiate at a higher rate than objects at low temperatures. If you hold an ice cube in your hand, it is radiating heat to your hand, though it may not seem that way to your hand because it will be radiating heat to the ice cube at a much faster rate. This radiation given off and absorbed by objects at everyday temperatures is generally infrared radiation, wavelengths longer than visible light. Even though we cannot see infrared wavelengths, we can still feel the heat that's transferred by those wavelengths. So the question is, what determines the rate of heat transfer by radiation of an object? It turns out that it's proportional to a couple of things, notably the exposed surface area of the object and its temperature. The larger the exposed surface area of the object, the more energy it emits per second. Also, the higher the object's temperature, the more it radiates per second. You'll notice here that this rate is dependent on the temperature to the fourth power. This means that the rate increases quickly as the temperature increases. And it also means that you'll need to use a Kelvin scale for the temperature, since it's an absolute value and not a temperature difference. There are two other constants out front. Sigma in this case is a proportionality constant called the Stefan-Boltzmann constant. There's Boltzmann's name popping up again. This is generally given in text in units that include watts for the rate of energy transfer, but since we're using kilojoules per hour in this section, I've converted it to those units for your use. The final constant out front, E, is the emissivity. It's a measure of how efficiently a surface emits or absorbs thermal energy. Materials that we work with, such as human skin or water, are actually very effective absorbers and emitters, and so these values are close to 1. So what do we do with this? Well, the air radiates heat to the body, and the body radiates heat to the air. The point of this is we need to determine the net rate of heat gain or loss through radiation with the environment. Adding this up will determine whether the body is gaining or losing heat through this process. The air is radiating heat to the body at a certain rate that depends on its temperature, and the body is radiating heat to the air at the rate that depends on its temperature. Because we have a lot of like terms here, we can factor them out and simplify this equation. The rate of a mammal's heat transfer with its environment through radiation depends on the emissivity of the body, the exposed surface area of the body, the skin temperature, and the air temperature. Remember that those temperatures need to be in Kelvin. The final process that we'll look at is evaporation. Mammals such as humans can cool themselves through evaporation of sweat that's excreted by the skin. When sweat's evaporated, it takes a lot of thermal energy with it. It takes about 2,300 kilojoules to evaporate 1 kilogram of sweat. If you know how many kilograms of sweat have been evaporated, you know how much energy it takes. This is thermal energy that's lost to the body, so in our system, its value is a negative number, as is the rate of heat transport out of the body. Mammals that use this mechanism have the ability to sweat more if they are too hot, or to stop sweating if they don't need to remove any more thermal energy. So, we now have these 5 processes that can transfer thermal energy either to or away from an animal's body. We can calculate both the rates of thermal energy transfer, and if we know the time over which they happened, we can determine the amounts. We have now completed our model of the processes that add or remove heat from an animal's body. On the left, we have our simplified model, and on the right, we have the thermodynamic equation derived from the first law of thermodynamics that explains the relationship between the net heat gained or lost by an animal and the change in the thermal energy of its body. If we expand the left side of the equation, we see that the sum of all the inputs and outputs of heat. The right side of the equation is determined by the change in temperature of the body. We can also use the rates of heat input or output. That will tell us the rate of a change in temperature of the body. So when you come to class, you should be able to list the factors that affect the rate of heat input or output by radiation between the animal's body and the air, use the radiative thermal energy equation to calculate the rate of heat gain or loss to the air. You should be able to explain how evaporation removes heat from the body, and you should be able to state the full relationship between the net heat gained or lost and an animal's change in temperature.